Okay, welcome to this lecture on the Lorentz transformation. So in this lecture, we are going to modify the Galilean transformation such that it obeys Einstein's postulates, among which that the speed of light c is always a constant in all frames of reference, at least all inertial frames. So we're going to start again from a frame S here, and let's suppose that there is a single flash of isotropic light that is set off at the origin. So some flash bulb went off and emitted light in all directions at time t equals 0. And we can illustrate that here by this expanding sphere of light, the orange circle there. So this was frame S. We can measure the radius, or at least calculate the radius of that sphere that's expanding at the speed of light. And that radius is just the speed of light times the time since the flash happened, so c times t. But if I square it, r squared is ct quantity squared, that's also going to be, in terms of the coordinates, x, y, and z. X squared plus y squared plus z squared in 3 dimensions. In other words, the 3D analog of the Pythagorean theorem. So I can relate that radius, which is ct squared, to the spatial coordinates x squared and y squared and z squared, that sum. Now, suppose you weren't the only one seeing this flash of light in your reference frame. Suppose that that flash of light is observed by another frame S prime that was traveling along the horizontal direction, and it just happened to coincide with the origin at time t equals 0 in its frame. So the same phenomena, same event, a flash of light, was seen by this other frame S prime, this green one that I'm showing over here. But this green frame is traveling across the screen to the right there, but it saw the same expanding sphere of light. What can we conclude? Well, by Einstein's postulate that the speed of light is always a constant, the outgoing sphere of light as seen in frame S prime, which remember was coincident at time t equals 0 with the first frame, it should see an expanding sphere of light in its frame as well. So if I illustrate that, we see an expanding sphere of light in its frame, even though it was moving by the first frame. It sees the exact same phenomenon, an expanding sphere. And it will have its own radius r prime. That's related to the speed of light times the time in its frame, ct prime. Quantity squared is r prime squared, and that's related to the sum of x prime squared plus y prime squared plus z prime squared. Okay, so we're going to use this contrived example to figure out how to derive the Lorentz transformation. Okay, now, just as we saw earlier in the previous lecture on time dilation and length contraction, we're going to expect that coordinates transverse to the direction of the velocity v of the reference frames with respect to each other will not be affected by the transformation. It's only coordinates parallel to that velocity vector. So namely, y prime will be y and z prime will be z. Recall that those transverse directions were not affected by length contraction in a previous lecture. But the coordinate parallel to v, the velocity vector for one frame relative to the other, will be affected. But let's at least assume it's a linear transformation, okay? So that means we'll let it look something like the Galilean transformation. We'll have x prime equal x minus vt, but we'll put in a factor k in front. Likewise, the inverse transformation for x will be like the Galilean transformation, x prime plus vt prime, measured in the prime system, but we'll put a factor k prime there. But wait a minute. Can k and k prime really be different? The transformation equation should have the same form, meaning as physics equations. There's expressions that go from one reference frame to the next. We can't have k be 20 and k prime be 35, for example. They should have the same form. There's no special reference frame. Only the relative velocity matters, so this sign of v matters, but that should be the only thing. So by that argument, we'll say that k prime must be k. They have to have whatever that factor is, they should be the same factor, okay? Okay. So now let's consider the outgoing light propagation from the flash at time t equals 0 as it expands out along at least the x-axis. Okay. So we have our expanding sphere of light here. It expands in all directions, but let's just focus on the x direction here. We will let y and z be 0 in this frame S. So that where that red arrow is, we're just calculating that distance along the x-axis. And, well, in frame S, that's just the speed of light times time measured in that frame, ct. But remember, the moving frame S prime saw the same phenomenon. So in its frame, x prime would be ct prime. Those are just two symmetric fundamental relations. But let's now plug those into the transformation equations I just wrote on the previous slide. For example, to go from x to x prime, we had this linear transformation. X prime is k x minus vt. But we are going to plug in that x is equal to ct here. So we're plugging that in, and that gives us the ct there. So we have k now times ct minus vt. But now I can just pull out, obviously, time out of the binomial, because both factors have time. And let's just go ahead and pull out a factor c. Oh, sorry about that. I've lost my screen again. Let's try to get back to where I was. Where did we go? Expanding sphere of light. Radius along the x-axis. And we plug those into our transformation equation. Okay, so I'm back to our rest. Apologies for that. Without the markings now. But okay, so we have kct minus vt. Pull out the c and the t. But I pulled out one too many c's, so that's why I've divided by c over here. All right, so just to recap, we took x equals ct. We plugged it into this x here, and that's the ct there. Okay, let's do the same thing for the other transformation equation. That is that x is equal to x prime plus vt prime times k. But now we're going to plug in for x prime, and we're going to use that relation there at the top. So we're going to have something quite similar. The only thing that changes here is we have a plus sign here, so we have a kct prime, and we have 1 plus v over c. Okay, all right. Okay, now let's plug these into the light propagation equations, which are the ones that are right up here. So we have that on the underlined purple, ct prime equals x prime. Here we go. But we just worked out that x prime is kct 1 minus v over c. Kct quantity 1 minus v over c. So I can solve for t, and I can cancel something here, right? I can cancel the c on both sides, here and here. And so I have that t prime is just kt 1 minus times the quantity 1 minus v over c. And we can do the same thing now starting from the underlined red, that ct equals x. So here's ct equals x. But we're going to plug in for x from this expression here, kct prime times the quantity 1 plus v over c. Do the same thing, and I get something very similar. I'm just swapping the primes, and then I flip the sign of v from minus to plus. All right, now let's do this. Let's plug the equation for t prime into the equation for t. So we're going to go from t prime here and plug it into the one below. All right, so let's see what we get. We're going to get t. So now I'm going to get two factors of k here. I'm going to get k squared, and then there's a t coming there. I have this 1 plus vc, that's this term here. And then I have that 1 minus vc, and that's that term there. All right, I can expand all that out. That's two binomials, 1 plus something times 1 minus the same thing. So it's tk squared, 1 minus v squared over c squared now when I multiply those binomials. And what does this tell me? The only way this equation can be true, that t equals t, k squared 1 minus v squared over c squared, is that k squared times 1 minus v squared over c squared better equal 1. Right? Otherwise I don't get the right thing. So that means k squared has to be 1 over the 1 minus v squared over c squared. So if k squared is 1 over that, the square root of k squared, which is k, has to be 1 over square root 1 minus v squared over c squared. So that equals gamma. So guess what? We just figured out that this factor k in front of the equation had to be gamma, which is shorthand for 1 over square root 1 minus v squared over c squared. So the modified transformation equations for the spatial coordinates are, replacing k with gamma, is x prime in the prime frame is gamma times x minus vt in the unprime frame. And x, going the other way around, is gamma x prime plus vt prime. And the transverse directions to that motion are unaffected. Y prime is y, and z prime is z. But wait a minute, what about time? We've only transformed the spatial coordinates. Are we done? Can we assume that t prime is equal to t? Probably not, because we talked about time dilation, right? So those the time variables also need transforming. So let's see how we could work on that. Well, we can take this x prime equation here in the Lorentz transformation and plug it into the inverse here for x. So let's just do that. Okay. And if we do so, I have x prime is gamma times, and then for everywhere there's x, I put a gamma x. I'm plugging the x prime equation into the equation for x. So I have x equals gamma, and then everywhere there's an x prime, I put gamma x, so there's a gamma x there. Then I have a gamma minus vt, so there's the gamma minus vt, the gamma minus gamma vt, and then I have a vt prime that's added here. So that's plugging this x prime equation over here to the right. Now let's solve for t prime. Okay, so let's use the right side of the screen. So let's put everything that's not t prime on one side of the equation. So I have an x here, so there's the x. This is going to be gamma squared x, but putting it on the left side of the equation means a minus gamma squared x. Then I have a minus gamma squared vt on the right side. Putting it on the left side means it switches to a plus gamma squared vt, and then that's it. Then I have a gamma vt prime that stays on the right, which I can slightly summarize by just pulling out the factor x and have 1 minus gamma squared here for these first two terms, and then the rest, the gamma squared vt and the gamma vt prime here on the right. Okay, but I want to try to make a relationship for t and t set equal to t prime. So let's now expand out this piece here. Gamma squared is going to be 1 over 1 minus v squared over c squared. So this denominator equals the gamma squared. So that's why there's a minus 1 and a gamma squared in the denominator here. Well, the gamma squared is not in the denominator, but the 1 minus v squared over c squared is. But if I have a 1 here, then I've got to put the denominator in the numerator. So that's the 1 minus v squared over c squared. So this piece here, let me go ahead and just show it in the pen. This piece here, 1 minus v squared over c squared, that's this 1. All right, but now I can try to simplify things because the 1 here cancels with the minus 1 there, and I'm just going to have a minus, and then there's a v squared over c squared, and then x, and then down here was just the gamma squared. And then I still have the gamma squared vt to add to it, and that equals gamma vt prime. So now let's try to divide by gamma v everywhere to isolate t prime. So I have t prime equals 1 over gamma v, and then the stuff on the left here, the minus gamma squared x v squared over c squared plus gamma squared vt. Long story short, because the gamma v, we can show there's a gamma here that cancels with 1 power there, 1 power here. There's a v that cancels with 1 power here and cancels this v there. And I'm going to be left with just t prime equal to gamma, because there's 1 power of gamma left here, times t. And then there's 1 power of gamma there. Sorry, not a power of gamma there. Yes, there is. Gamma v times x over c squared. So a little bit of algebra there. So this boxed equation here is the final expression for t prime in terms of time t, which is not so obvious, right? It's pretty messy. It's mixing in the space and time components. So let's summarize what we've learned. We're trying to transform from one, let's say from frame s prime here in green to coordinates in frame s over here on the left, and vice versa, coordinates in frame s to coordinates in frame s prime. This is the generalization of the Galilean transformation to obey relativity, so this is the Lorentz transformation. And we see that the orthogonal coordinates are not affected. X coordinates are along the direction of motion in terms of that velocity v, and it's just a difference of plus or minus v going from one system to the other. The time does mix up space and time coordinates, so it's this more complicated part here. And gamma is this shorthand for 1 over the square root of 1 minus v squared over c squared. So there you go. It looks like the Galilean transformation, but we have a gamma in front for the transformation of x and x prime in terms of the opposite coordinate. And time is not universal. There's a gamma that comes in there, and there's even some spatial component. And by the way, so the Lorentz transformation is sometimes called a Lorentz boost when we go from one frame to the next. If we want to calculate the coordinates in another frame, we call that making a Lorentz boost into another frame. Let me mention some features here of the Lorentz transformation now. So I summarize the equations here on the right. X is gamma, x prime plus vt prime, and so forth. First of all, we will recover the Galilean transformation if we let either the speed of light go to infinity or the velocity of the reference frame, one frame relative to the other, go to 0. Because in either way, when I have gamma being 1 over square root 1 minus v squared over c squared, if v goes to 0 or c goes to infinity, this gamma just becomes 1, and I recover exactly the Galilean transformation. Even this term here on the right, with c going to infinity or v going to 0, goes away. So no surprise, we had the Galilean transformation before, because for velocities much less than c, we don't notice these effects. Also, as I mentioned a moment ago, the space and time coordinates are mixed. Here I have time coming into the spatial component x, and here I have the spatial component x prime going into to calculate the time. And what that means is that two events that are simultaneous in one frame s prime, say at time t prime equals 0 and at positions x1 prime and x2 prime, they're not going to be simultaneous in another frame s, because t1 and t2 will not be the same times. So it may have looked simultaneous in one frame, but in another it'll be two different times, just because of this mixing up of the spatial positions and time coordinates. So simultaneity is not invariant. It's only in one specific frame. And also note there's no change in form of equations from one frame to the other. They all have the same expression, just relative velocities matter. And in fact, from this more general set of equations, one can derive time dilation and length contraction from this transformation. One way to see it is, suppose we have a clock of period t prime that sits at rest in frame s prime at position x prime is 0. So the clock's at x prime is 0 and has a period of t prime. If we want to know what the time is in frame s, I use this last equation for time over here on the right. But x prime was 0, t prime is what it is, but I see a gamma t prime to get the time in the unprimed frame. So t is gamma t prime. So I do recover time dilation. Likewise, one can also work out length contraction using this Lorentz transformation equation. Okay, there you are. There's the Lorentz transformation in all its gory details for you to be able to calculate and going from coordinates in one reference frame to the other.